What's up, everybody? This is Matt Brown with part 4 of our Enterprise IoT Pentesting series. Today, we are going to take a microscope to data in transit and look at how we can find vulnerabilities in the network communications of these IoT devices deployed in your enterprise. And so, without further ado, let's jump over to our slides. So, like I said, part 4, if you haven't checked out the rest of the series, definitely go ahead and do that. Today, we're going to start by talking about a couple of common network architectures that exist in enterprise IoT devices. And so there are many different variations of these architectures. You could definitely list more. Please do so in the comments. But I want to compare and contrast two architectures, and there's going to be a point behind this. So the first architecture we're going to look at here is what I call a weakly connected IoT architecture. This is where we have our device over here on the left of our diagram, and that IoT device does not directly communicate to any internet or any traditional kind of IT systems directly. Instead, there is some kind of a middleman application. Typically, this is going to be on a phone application, and then some type of communications is going to occur between that mobile app and the IoT device. Very commonly, you'll see this be Bluetooth Low Energy, just because all smartphones today are guaranteed to have a highly functional Bluetooth Low Energy stack, and it makes it really easy for developers to write an application that's going to work on all mobile devices and can communicate with their device and pull data off of it and push data to that IoT device. And then that mobile application can then communicate with some cloud servers, APIs, backend systems, you name it. But this is this weakly connected architecture where the IoT device itself is not really performing any network communications, right? It's happening via some other channel like Bluetooth or other kind of data transfers, and then it's relying on some kind of a client application to pipe that data where it needs to go to the cloud. And we can contrast this with what we're going to focus a lot more on in this section, because it's really where network communications come into play, and that is a directly connected architecture. And so here we have the IoT device is in the middle, right? It is both potentially offering up network services. We're going to talk about that in the next video, in part 5 of this video series. And so that's where, think your Wi-Fi router at home. It has like probably a web server on it that you can use to configure that device. In enterprises, again, oftentimes there's going to be a graphical user interface in the form of a web application that is going to run on that IoT device that allows you to configure it and do everything you need to do to manage that device. And so you will potentially still have mobile applications, desktop applications, other types of apps that will connect to that IoT device, kind of like we saw before, right? So that is similar to the architecture, the weakly connected architecture. But in this architecture, the IoT device itself also can communicate out to cloud servers directly without kind of a proxy system implemented in a mobile app or some other kind of application. So here we see kind of the breakdown of the next two areas of an IoT pen test that, as a pen tester, I want to look into to find vulnerabilities. Like we said, that first part, the network services that are hosted on the device, we're going to look at those next time. But I want to talk about the difference. So generally speaking, with a TCP/IP device, this IoT device here, you're going to call what's a network service and what's network communications, right? Well, if the IoT device is acting as a server and it's hosting an application running on a server, and some other device acts as a client and connects to that service, those are going to be network services. Whereas when the IoT device acts as a client and makes an outbound connection to some server, whether that's a server on a local network or it's a cloud server, some backend API system, those are going to be network communications. And that's what we're going to target in this video. Those network communications when our IoT device reaches out to its cloud servers. And there's a bunch of little nuances and vulnerabilities that can come into play here. So to study all of these network communications, there's lots of different setups you can use out here. This one is a tool that I've built, and when I say a tool that I built, it's really just a bunch of scripts that automate open source projects that other awesome developers have written. And so we are going to talk about this a little bit, and then we're going to use it in our case study on our UniView camera over here on the bench, our commercial security camera, that we are going to use this system to capture traffic. So I want to do a deep dive of this. If you've watched some of my videos before, thank you. If you haven't, definitely hit that subscribe button for more content like this if you're enjoying this kind of educational content. So this system, again, it's kind of, you know, duct taping together a few different open source Linux utilities on a Linux host system. So it could be a laptop, a desktop, whatever. You could run this on a Raspberry Pi if you wanted to. So here we have our Linux router, which is really just our Linux PC that we're running all this software on. And the goal of this is to have a flexible system where we can capture traffic passively without performing any kind of modification attacks. And optionally, we can flip on those man-in-the-middle attacks. And so this is going to allow us to do that. So first thing we have here is this application host APD. This is a open source tool. Actually, probably most Wi-Fi routers out there use this tool under the hood to host access points, Wi-Fi access points. And so we are using the same tool that so many routers out there use to spin up a wireless access point, because many enterprise IoT devices are wireless based. And so that gives a wireless network where you can configure, you know, the SSID, the password, the encryption type, everything that you want to play around with as a security tester to allow those IoT devices to connect. Additionally, we have the option to have an Ethernet interface, and that's what we're going to use in our case study today, because our device is power over Ethernet and communicates over Ethernet as well, obviously. So that is going to all connect to this BR0 bridge interface in this setup. And then on that interface, we are going to run DNS mask. Now, DNS mask can do a couple different things. Obviously, as the name probably implies, it can host a DNS server, but we're actually not using it for that. We're using it as a DHCP server. So on the LAN side of our test network here, on this BR0 interface, we will hand out IP addresses within a certain subnet range, and that will act as the local network for our IoT devices to live on. And then let's ignore this IP table stuff for a minute, because I'm gonna circle back to that. Because then on the WAN side, this interface is going to be whatever interface on our Linux computer has internet access. So you just look at whether that's Wi-Fi or Ethernet. You are going to need one additional wireless interface and Ethernet interface. I highly suggest USB-based ones. That's what I use. So I have a USB to Ethernet adapter, and I have a USB wireless card that are implementing both of these interfaces over here on the LAN side, and then on the other side I just have my computer's standard Ethernet port providing the WAN access. And then we get back to IP tables. So IP tables, if you're not familiar, is the kind of built-in Linux facility for managing firewall rules. And one of the cool things we can do with these firewall rules is, as we're passing traffic between our WAN and our LAN interface, we can set certain rules to redirect certain traffic, you know, where we can filter based on source or destination IP or source or destination port, oftentimes both of those, where we can say, hey, you know, if we have outbound traffic for port 443, right, which is commonly HTTPS, TLS communications, let's send that to a tool called man-in-the-middle proxy, for instance, or there's other SSL proxying tools that we can use to attempt to perform man-in-the-middle attack on SSL traffic. So this whole setup is very flexible. We can plug and play different tools into this setup, but we'll take a look at that more in our case study. And to be clear, an IoT pen tester doesn't have to use this setup. They can use their own, but they are going to want to do two things: have a way to passively monitor all traffic that comes from the IoT device that goes. So if we kind of go back a slide here, so we want to monitor all the traffic that is sent out from our device to the cloud APIs, and we want to track all the responses from any of those systems back to our device. But additionally, we want to perform some attacks that are going to go beyond that. We'll get to that in the next slide. So Wireshark, obviously, if you are in the cybersecurity industry, you have probably heard of this tool. It is the gold standard for taking packet capture data, whether it's saved or live captures on an interface, and you can perform a number of filters, and you can look at every packet that is sent over a certain interface that you have the permissions, of course, on your machine to sniff. So what are we going to look for in Wireshark if we we have this enterprise IoT device? What are some of the things we want to look for? Well, first of all, we want to look for any unencrypted communications. So obviously, clear text HTTP is going to be the most common clear text protocol out there. But especially on these IoT devices, you're going to find some weird custom designed protocols that the developers, came up with because they thought if it was super secret and non-standard that the attackers weren't going to be able to figure it out, which is, spoiler alert, they're not. That's not how things work. But that's something we want to look for in those streams. And then we want to look for also encrypted data streams like TLS. And so these are going to be targets for our man-in-the-middle attacks, where we attempt to pretend to be the server and check if the client, in this case, again, our network communications, our IoT devices acting as a client, connecting to a server in the cloud or somewhere else, and we want to pretend to be that server. And so, yeah, we'll get into that more in a little bit. But these right here are some of my most used Wireshark capture. No, excuse me. They're display filters, not capture filters. The capture filters use a different language, and I hardly ever use capture filters. I use display filters, and they are, as you can see below. So DNS, obviously, like any DNS requests that the device is making, are going to be a huge hint as to what cloud systems are being communicated with. And then HTTP is a quick filter that you can throw in to see if there is any clear text HTTP traffic. And then we have TLS. So obviously you can just type TLS and use that filter to filter all TLS traffic. But what I really like to do is I like to use this TLS handshake type equals 1. And what that does is that is the client hello message. So each time a TLS session is initiated, the client is going to send a client hello message to the server. And so that cleans things up for me in Wireshark and doesn't show me like a million TLS packets. That's all the encrypted data that I can't see inside of anyway in Wireshark, unless I do some other stuff. It just shows me one packet per connection. So I can be like, oh, okay, it connected to this server A, B, C. It's a nice little filter there. And then obviously this one is, okay, so we said we want to look at DNS, which by default operates over the UDP protocol. And then what I like to do is after I've looked at some of the DNS messages, I like to throw in this filter to say, show me all UDP traffic that's not 53, and that will quickly help me find some potential custom UDP protocols that are communicating to some kind of backend system. So that's always a good one. And then this last one here is kind of the similar thing, but in the TCP world. I'll be honest, I don't use this one that much, but it can be useful to find, again, non TLS type of TCP traffic that your device is sending. If there's any really odd ports that it's using, this should grab it. So moving on from that passive kind of packet sniffing to testing a active man-in-the-middle attack. So to do this, there are a number of different tools that I will suggest. The first one is Cert, and the cool thing about Cert, so both of these tools are going to act as a transparent proxy. So they are going to, when they get that client hello TLS message from a client, they are going to look at the host name and they are going to forge a server certificate, like a non-trusted server certificate for that domain, for that subdomain or whatever. And that server will act these programs will act as if they are the host. And then what should happen is that the client should reject that connection, because it should say, whoa, 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 this certificate is not trusted based on some kind of a CA root of trust that it has, that it expects. So that's what we're testing. That's the crux of what we're testing here. And these are a couple of awesome tools to do that. And so Cert is awesome because Cert, what it does that man-in-the-middle proxy does not do, is that it will try to do a man-in-the-middle attack. And then if it fails, it will stop doing the man-in-the-middle attack for that host while that session is active. And so that is super nice on IoT devices, because oftentimes what will happen is you'll have a device that will communicate with server A, and once it receives a successful response from server A, then it will communicate with server B or C or so on, right? But if you are always man in the middling and it's always failing to connect to that first server, well, it's never gonna, its logic is never gonna move on to communicate with the next server. And what if the next one is vulnerable to a man-in-the-middle attack, but the first one isn't? So this is an awesome tool that lets you iterate through all of the hosts, because you will be surprised that on an IoT device, it's a big project, there's multiple developers, right? Where there are different HTTP TLS clients. There are different client libraries being used to do these cloud communications, and one will be vulnerable and one won't, and this is an awesome tool to sort that all out. Man-in-the-middle proxy is a go-to tool that I use as well, and you can find the documentation there on GitHub. And again, all these tools are going to forge those server certificates, and let's get into that a little bit, because one of the big kind of misconceptions I see out there are the difference between certificate validation and certificate pinning. And especially if you are kind of from the bug bounty world like me, you can kind of get a little queasy and be like, whoa, aren't you talking about a vulnerability that nobody cares about? Nobody cares about certificate pinning. And they will confuse certificate validation with certificate pinning, and understandably, because sometimes people do use them interchangeably, or in my opinion, use the wrong term to when they're trying to talk about one thing or the other. So the difference is, on the left in this diagram, we see what certificate validation is. And this is where we have a root CA. So in the kind of the public key infrastructure system, there are certain root CAs. Now you might have your own private root CA, which is great, or you might use a public one. Doesn't matter. But that server certificate is at the top is going to be signed by an intermediate, and that intermediate CA is going to be signed by the root CA. And the server will give all of those. It'll usually give the server and the intermediate, or maybe just the server, and say, hey, here are the certificates. Here's who I am. Here's my proof that I am who I say that I am. And then in certificate validation, the system is going to say, oh, you gave me the server certificate. Is this signed by an intermediate CA that I trust, or one that you sent me? And then it will say, well, are those signed by the root CA that I trust? The trust in certificate validation starts at the root CA. Certificate pinning is different. Certificate pinning says, yeah, I don't care about root CAs at all, intermediates, whatever. All I care about is that the server certificate is exactly the certificate that I expect. And there are different ways of implementing this certificate pinning. Oftentimes you will see certificate pinning being done in a mobile application context, and it's usually done, well, there's multiple reasons you could do it. But in my opinion, the main reason it is done is to annoy people like me who are bug bounty hunters or pen testers. And it's to get in the way of, on our own phone, being able to proxy the TCP traffic and sending it to a proxy so we can see inside of the encrypted communications, right? So that's certificate pinning. And the reason why people kind of get these confused is because certificate pinning, pretty much on every bug bounty program out there, is going to be out of scope. They're going to say, we do not want you to report a bypass of certificate pinning. And the reason is because it's so easy to do. Like, there's always a way to bypass certificate pinning. So, but, certificate validation, this is a core issue. If you are not doing certificate validation, then a man in the middle can just pretend to be the server, and and then that will be accepted by the client. Now, where the confusion happens is because, technically speaking, certificate pinning, it's like a Venn diagram where certificate pinning is a subset of certificate validation. So if we are missing certificate pinning, but certificate validation is being performed, that's not a vulnerability. But if we're missing both of them, then that is a vulnerability, and we need to report that. So I'd love to talk about that more, and please leave comments if you'd like me to do like a full deep dive sometime on TLS. I love talking about that, honestly. But we want to keep moving and not this be an entire lecture on the TLS protocol. So without further ado, let's go over to the workbench, and we're going to do that really fast, but we're just going to explain what's going on. Obviously, Ethernet network. This is plugged into, as we talked about before, a PoE injector here, and then this, the other end, which is over here, is plugged into a USB adapter that is going to be used for our man-in-the-middle router setup. So again, here is the GitHub link. I will have this linked in the description of our video if you want to check out this tool. Again, there's other tools out there you can use. You don't have to use my tool, but we have the same diagram, and we are ignoring Wi-Fi. This is not a Wi-Fi based device, but again, we have our IoT device, our camera over here, our UniView commercial security camera, plugged into the Ethernet interface. That is going to show up on BR0. So today, we're just going to do some passive sniffing, and that's all it's going to take to find some vulns on this device. And so we're not messing with the IP tables rules at all. So let's come over here. And if you remember, last time on our device, we were able to get an unlimited root shell over UART here. Clear command doesn't work. And we can see that our device is picking up this IP address. So over here, I am running man-in-the-middle router, and it's, it is hosting my access point, which again is not even being used because we're not using Wi-Fi right now. But, and I don't have any IP tables rules active. So I'm not gonna restart that because then it would kick me out of Wireshark, which is annoying. But what we're going to do is we're going to come over here and we're going to say IP address in Wireshark. So we're actively sniffing. We're actually going to hit stop for a second. We're going to set a display filter of ip.addr equals, and then the IP address of our camera. And so this is going to show only traffic from our camera. And we are going to turn that off and on again. And we're going to let the device, we're just going to sniff all the traffic from boot up of the device. This is one of the first things I do when I get my hand on an IoT device. And you would be amazed the bug bounties I have earned on, the bug bounty programs of top tier tech companies out there in the world. just by doing this, just by observing what happens when the device boots up from a network perspective. So here we can see that the device is booting up again. It looks like it's already booted. And oh man, we've already got some traffic. Sweet. So right out of the gate, we see the DHCP protocol. It's the first thing we see because that's how the camera says, hey, is there a DHCP server out there? And then again, like we said, man-in-the-middle proxy, we are using DNS mask to provide that IP address. So here it says, yeah, here's your IP address of, something. Aha, there it is. Your client IP address is, .26, which we already knew. And then, quite interestingly, the device actually pings the gateway. That's kind of interesting. It pings the gateway, and then it starts doing some DNS requests. So it's going to send a DNS request. If you don't know this off the top of your head, like I do, actually, let's make this bigger. Right here to 8.8.4.4. That's like Google's DNS server. And it says a DNS request for the host www.star4live.com. This is a system that is put out there by Uniview for basically its cloud connection, right? So we are going to be seeing communications that allow the camera to facilitate being, viewing your video stream wherever you are, not just on the same local network. And so it does that DNS request. There's some kind of like a CNAME thing, and it says, okay, here's this ELB, so it's being hosted in AWS. We can see there. And then we see some things that we probably shouldn't see. So we see traffic to port 80 on this cloud server right here. This is not a local IP. This is a public IP. So these communications are going over the public internet. And then we see a clear text HTTP message right out of the gate. I'm going to, just to hone in on this clear text communications, there might be some other interesting things, but for the most part, that is the thing we're looking for here. So I'm going to, in our display filter up top, I'm going to say and HTTP. And here we can see a number of HTTP messages that have been sent in clear text over the internet to these cloud servers. So we are going to go ahead on the first one, and we're just going to right click, follow HTTP stream. And then it gives us this text representation of the request and response. So here we can see that we are sending a post request out to the cloud. We have this some kind of device identifier here, so probably the serial number or something like that, and a bunch of other information is being sent, and then we get the response from the server, which is amazing. So we get the, some information. I see STUN key, device tunnel configs. So there's a bunch of configuration information for the camera that is being sent in clear text back from the cloud, to the camera. So that's one request. Okay, so I'm gonna back out of that because there was another request here, a post that, I don't know if that's the same message. Okay, so yeah, this is like same keep alive thing where it gets something back. I just want to see. Yeah, that's kind of the same data. Sometimes, actually, okay, I think I can kick it into sending like some other unique packets by just logging in here to the web interface. Okay, so I think all I have to do is just that, and then, okay, now we're gonna see a bunch of traffic from like my machine to the cloud or whatever, not to the cloud, directly to the device. So we probably need to filter that out. Okay, so we're gonna say and IP.adr not equal to 192.168. Okay, so I'm gonna basically say like don't show traffic that includes my host system, and that should get some stuff filtered out here. Okay, here we go. So here's another request that we see here, COS info. And yeah, let's follow that stream as well here. So again, we're posting some more stuff, and we're getting some more data back. That doesn't seem as sensitive. But again, all these communications are happening in clear text, which means that a man-in-the-middle attacker could inject data, like they could change the response that's being sent to the IoT device. Likewise, you could do things to attack the cloud server this way by messing with the data that's being sent to the cloud server. All this stuff in clear text is not a good time. So all this other, yeah, there's a bunch of stuff in here that looks like it's, I mean, it is clear text HTTP. It's just I generated it here with our camera. There it is. But I think you get the point. Thank you for watching this video. In this video, we focused on the network communications, where the IoT device is communicating out with the cloud or some other system. Next, we are going to turn to the services, the network services that are running on the device itself, and some potential clients that will communicate with those services. So thank you for watching this video. Be sure to subscribe if you enjoyed this content. Thank you and have a good day.